Okay, so let's. Are we missing some people? We're missing like a bunch of people, aren't we?
Like three.
2 or 3? We might have to do an attendance quiz. We'll see.
Yes, please do. We joked about it at work this morning, and someone's not here now.
Do we want an attendance quiz?
It's easy.
It's just an attendance quiz.
What's your name?
Points.
What do you write down? I am here.
Yeah, somebody pass around a piece of paper, just put your name on it. Like one person donate a piece of paper and everybody put your name on it.
I got it.
Good job, I almost want to add our Slack channel and be like, thanks, guys.
Take a
Wait till the
picture
end of
of
the
it.
rest of the day. They don't show up.
All right. Oh, what am I doing? I'm not creating a new slideshow. We're talking about semaphores. All right. So, kind of getting back to this idea of resource protection. We've been talking about this somewhat at the, I don't know, what's up? Oh, somewhat at the high level about protecting our list of connected clients. That we want to make sure that that guy is always, that nobody tries to write to that when it's in the process of changing, right? So for example, when the server is adding a new person to that connected clients thing, we don't want any of the threads to be able to grab that and write to it. We want them to be delayed somehow, hence guaranteeing that when a thread finally has access to that array of integers, that they're dealing with the most up-to-date version of it. Okay? So really this falls into this category of protecting a resource. And we have this idea called mutually exclusive access to a resource. Now, some resources we can have multiple, like for example, we might have an example where we have a resource that can have up to 3 people using it at once. Something like that. I don't know, maybe that's like you have a soda machine, something like that has, they've 10 different sodas, so as long as people wanted different sodas, 10 people could potentially, because I think you can push more than one button at once, right? I think that works. Yeah, so 10, you know what I'm talking about, right? You can get Coke and Sprite on the same machine at the same time. So we can decide we're going to let multiple people have access to that one resource simultaneously, as long as they're dealing with different portions of the resource, right? So now you might have multiple levels of protection for a resource like that. We will let more than one process, more than one thread access the soda machine at one time, but only one person can access the Diet Coke button at one time. All right, so as long as they're willing to go to a different soda, we'll let them do that. All right, so we need to give them mutually exclusive access. Now, we have to think about how is this accomplished. And this goes back to our conversation about processors, where on a CPU, we think of this lowest common denominator as being like a CPU cycle, right? So how long does something take to accomplish on a CPU? And we've talked about our CPUs as being this like collection of magic tricks, right? Now, the reality for us is that those magic tricks aren't all created equal in terms of execution time. I like to think of CPUs as, they're called data paths, but I like to think of each of those data paths as being kind of like a program written in hardware, okay, where you have gates and transistors and things like that happen to go through, and that gives you your output. So you feed electrical signal input, it spits out an output. All right, and the complexity of what's in the middle there is different for the different magic tricks, right? But we would typically, I think we can always say it's possible modern software might be faster than some very, very old hardware, but generally speaking, hardware is always going to be faster than software. Hence, that's why we have hardware-based processors and not software-based processors, and that's why we think of things like virtual machines as being a convenience but a slowdown. right? Because we're abstracting something through software. So point is that each of those magic tricks that we might call upon on our CPU might have a different runtime. If we're measuring runtime in terms of the number of CPU cycles, where 1 is the minimum number of CPU cycles something can occur in, we usually call this kind of runtime atomic. So atomic runtime is when something occurs in 1 CPU cycle, or as if it occurred in a single CPU cycle. And that's kind of the catch here. It might be very difficult for us to have something that does anything. Well, it might be. It really would be very difficult for us to have a magic trick on the CPU that is meaningful at all, that does something at all, that actually occurs in a single CPU cycle. That means that it's a very simplistic, very simplistic solution to a problem. Very simplistic data path, right? To the point where it's probably not solving a real issue. So now we have to think about the second side of this, is how can we make something act like it's occurring in a single CPU cycle? All right, so this comes down to how can a CPU be interrupted? Interrupting the CPU. So based on what we know from operating systems and things like that, what are the different situations that a CPU can be interrupted? Okay, if we do I/O, so if a program needs to do I/O, it gets interrupted because there's a context switch off of the CPU for the guy to go get in the line for I/O. What else? Yeah, out of time. Okay. So out of time on CPU, it's going to be kicked to the current process. Current PCB will be kicked out due to being out of their allotment of time. What else? So we got to drag this back towards this idea of sharing a resource. So when we had single processors, single core processors, this was an easier problem to solve. In fact, life was almost always easier, but it was also slower. Okay, right? that's the trade-off. You know, with great power comes great responsibility. Our operating systems, it got a lot more complex when we started throwing more cores in there and more data channels to your memory and all this other stuff. So with that in mind, if we have 2 processes running at once, 2 threads potentially scheduled at the identical time because we had more than 1 core able to run them. Now all of a sudden, the idea of an atomic operation has completely changed, right? Because now we're not thinking about an atomic operation on a single CPU. We're thinking about something occurring such that none of the other CPUs can access a critical area in our code at a particular time. And that's no longer controlled by a single CPU's ability to not let anybody else butt in. Does that make sense? Because we have, in a quad-core processor, we have 3 other CPUs that are running wild that potentially can try to access the same part of memory, something like that. Okay, because when we think about memory, memory is a centralized resource. Okay, so most of the time when we're talking about protecting a resource in a computer, we're talking about like a variable that lives in memory someplace, right? So if we kind of draw a picture, memory's always red, right? Makes sense. So this is our RAM. It's this guy sitting here, so whatever it is, 8 gigs, 16 gigs, however much RAM. Then we have our CPU. And we'll just go ahead and pretend this guy's a quad-core CPU. Is that the Microsoft logo? I wonder how much the guy who came up with that got paid. The irony is I just did it in Keynote. which is an Apple product. Okay, so this is our quad core processor. We'll just say this is a process of core 0, core 1, core 2, core 3. Kind of unimportant for this example. All right, so all of these guys are running on their own time. They have their own scheduler, things like that. And obviously we can expect that things get pretty complex when you're trying to schedule across multiple cores. Not our problem in here, right? It's an operating system. Somebody smart did that. Okay, that's a thing that's already happening. All right, but the reality is that we have our single bank of memory. And this guy is a resource in our system. It's a resource that happens to be able to store stuff relatively quickly. Correct? Store stuff relatively quickly. Now, is this our fastest form of memory? Okay. What lives between here and here? So we have cache memory, L1, L2, L3 cache on on modern processors, things like that. For our example, let's just pretend like that doesn't exist. We'll just assume that everything's coming in from this single resource that will get us to our same endpoint. Okay, but there are ways of smoothing out. So effectively, this idea of mutual exclusion we're talking about today in hardware is, so from a computer architecture perspective, is solved, is lessened at the level of cache where we insert something here in the middle, where cores do not go to system memory immediately looking for the value they're looking for. They first look for it in cache. They first look for it in L1 cache, which will be the fastest place to find it. They don't find it there, they're looking for it in L2 cache. If they don't find it there, they look for it in L3 cache. And then the bailout is to finally go to RAM. Okay? So the hope is you hit RAM less often, because then you need to have some sort of floating resource up here that decides, well, what stuff needs to live in L1, L2, or L3 cache that also lives here? What should I load into those caches so that I have the best chance of the next time one of our cores needs something, it'll find it in cache rather than system memory? Make sense? The advantage of that is each individual core gets its own L1 and L2 cache. L3 cache is shared among all the cores, but L1 and L2 are on a per cache basis. And so if we blow that up to 2,000 feet here, we pretend like cache doesn't exist, we have a situation here where our bank of RAM is shared among all of these cores. They don't each get their own data channel to RAM, to their own RAM. Okay, so it's shared amongst all of them. So if we have some variable that's sitting in here, so let's we'll draw this will just be an integer. This guy's gonna be a 7. Okay, and integers are obviously yellow. Okay, can you disagree with that? You know I'm right. All right, so integers are obviously yellow, and so this integer is something that, let's say we have 4 threads that just happen to get scheduled across our 4 cores. Moon's lined up, processor's not busy doing anything else. 4 cores are each running one of our threads. If we want to even think about it in terms of processes, each process is running on there instead of threads. That would be probably more likely that all 4 would be running at the same time. But regardless, all 4 are running, and they're all interested in this integer. Make sense? Now, you have an issue, because sometimes these guys might be writing to this integer. Sometimes these guys might be reading from this integer. But we want this integer to always be accurate. So if this guy tries to read from this integer while this guy is trying to write from this integer, and this becomes a race condition, which we've discussed, this guy may or may not be able to change that integer before this guy reads from it, giving us an unpredictable result, right? We might not be grabbing the value we expect to get because we thought we had mutually exclusive access to that resource. And when we didn't, our logic might break. Okay? So we're here trying to protect this individual value that lives somewhere in memory against giving us bad reads or writes from 4 CPUs, in our example here, all because these 4 CPUs technically are sharing the underlying resource that value is stored in, and they have to figure out, how do I share this resource? Who gets access to this resource first? Who gets access to the resource second? And how do we stop them? All right. So we could put all sorts of stuff in there that, we decide, okay, well, we'll have a little if statement there. And I mean, the idea is that race conditions that we talked about before are kind of hard to reproduce. Because most of the time they don't happen just out of sheer luck, right? I mean, the more processing, the more simultaneous threads, the more simultaneous processes, simultaneous users, the more things that are going on in a computer, the higher the chance that you're going to have a race condition because everybody's fighting for system resources. But under a normal, hey, I'm using my laptop perspective, chances are fairly low that one will occur. But if it does occur, bad things happen. Makes sense? That means we still need to protect against it. Most of the time, if you park here at Concordia, you could probably leave your doors unlocked and it wouldn't be a big deal. Most of the time. Until somebody comes and steals your 8-track collection.
Happened to you?
Well, you think I have an 8-track? Okay, but I might. I bet you Dr. Locklear has an 8-track collection.
Park in the same spot every day. Are you telling me your doors aren't locked?
I don't park in the same spot, do I?
No.
Depends when I get on campus. If I get on campus early, I park closer to the building. If I get on campus later, I always park in that very
I
back.
see you in the back of the feed.
I think they're locked, but I don't know. But there's nothing. I mean, if you go in there, can you clean up my trash behind my driver's seat? It's like that's where I throw my my protein shake bottles when I'm done with them. And I just wait for the next time I'm going to have guests in the car before I clean it up. Nobody else is sitting back there. What's the big deal, right? I can only imagine what his car looks like. When I was in Florida this last time, there was this car. I've seen it there multiple times. This isn't like a one-off experience. I've seen this car over multiple years. There's this lady that lives in the same complex as my grandma who has this car, and it's got to be one of these like hoarders. Inside this car, everything except the driver's seat it looks like it's filled with newspaper. I mean, it's just wadded up garbage. This thing, it's not like, there are probably sweaters and stuff like that mixed in, but it's random stuff filling this car to the brim. Even up in the dashboard area, like by the windshield. She has this unbelievable. That's the back of his car. That's his whole car. I've seen it. You left it. You see my second car? Where did I put the extra junk? When I ran out of room in my car, I had to find more room to the other car. All right, so in any case, we can try all sorts of things to protect against this, and most of the time, we wouldn't even have to do it. Most of the time, we're not going to have a race condition. But since we rely on accuracy, we need to protect against race conditions because it might be bad if we have them. All right, so that's a matter of when we go and ask ourselves, is the resource that I'm working with here potentially going to have a problem of being changed when somebody else needs it? So the second we start, moving into the world of multi-threaded or multi-process type of applications where we have some shared resources across them, all of a sudden we start playing with kind of a danger zone. Right? And this is even kind of one of the reasons we go back to some of the earlier programming classes and we talk about, I usually use kind of the phrase for the almost the rationale from going to C++ to Java was C++ empowered the programmer to kind of make bad decisions. If they were a beginning type programmer, because you have so much direct control over memory, and we're seeing that in here. We're constantly throwing asterisks or ampersands or random stuff or little arrow things. We're putting all sorts of weird syntax on stuff because we're wiring through to the actual underlying memory where this stuff lives, right? You don't have that in Java. Java protects us from ourselves. So let's say most of the time that's good, but sometimes it's an inconvenience. All right, when it's an inconvenience, then it's a bigger inconvenience. But most of the time, it's not a major issue. So in an older language like that, the second we start passing around memory and we start spinning off threads or spinning off other processes, now we start having an issue with shared memory being overwritten by one or more, by two or more threads at the same time that might break the logic for something else. And that's when we have to start being concerned about protecting those resources. So you certainly don't need to dive into your Hello World program and decide that you're going to protect every variable you ever create. All right? Most of the time, that's a self-solving problem. But when we start talking about having multiple processes running or multiple threads running and sharing resources with memory, now we have to think about, do I need to protect this piece? So in our little example here, we're saying that this 7 is a very integral integer. It's an extremely important part to our upcoming space launch. Okay, this guy cannot be off, even by 1. It's a coolant thing you wouldn't understand. It's whatever. All right, so we got to protect this resource. And the issue here is that our underlying resource where this guy is stored is shared among all of these cores. So technically, all 4 of these guys can make a grab at this resource at the same time. Now, depending on what we know about access to this resource, we might say, oh, well, maybe this is a self-solved problem. Because if this resource is only letting one of these guys access it at a time, then I don't really need to worry about something that's stored in there because only one guy will be able to grab it at a time. Unfortunately for us, memory isn't one of those resources. That would slow our computer way, 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 way down, right? We're going to allow multiple things to try to access our RAM simultaneously because since it's hardwired RAM, as long as you're accessing different buckets, that you have a performance gain by letting 2 guys access it at the same time, right? It's just going to a bucket. There's no problem if we think about this as a big street. There's no problem with somebody knocking on the door of next door and knocking on your door at the same time because they're trying to access different values. Make sense? Okay. It's a little bit more complicated when you think about how RAM is actually wired because maybe your door and the door next door actually might still be on the same path, but close enough, right? We can look at it at the high level that way. All right, so we should allow that. We're not going to block people from knocking on a door anywhere on the street if somebody's at your front door. All right? So because RAM is not protected, so because multiple cores can access this resource at the same time, this guy is now at risk. And since this guy is now at risk and we've decided that we need to protect this resource, we have to come up with a mechanism that only lets somebody access this resource when we allow them to and relinquishes, almost locks the door, right? Okay, locks the door, relinquishes that lock when they're done. All right, so when we're modifying this variable, so if we kind of want to put another vocab term here, so we call this guy the critical section. Critical section. So this is the important code that is modifying, well, seemingly important code, modifying the, let's call it protected variable. So this is the important code that is modifying. We could say modifying / using. We might not always be modifying. We just want to make sure that if we're using it, it's not also being modified by somebody else. Okay? So this is the important code that is modifying / using the protected variable. Okay, that's the critical section. So what we want to do is we want to create a bouncer on either side of that critical section. Okay? So that we only let one person through the door at a time and only let one person, and that door then locks until the other door opens and that person leaves. That make sense? So picture would look something like if we have our critical section, it's probably a pink star. Makes sense, right? And we have our, what are my pictures? We'll go with this guy. These are our doors. So doors are skinny. Well, my next color choice is actually going to make sense. So right now, this resource is available. Okay, and that door is locked, so whatever. So this is our critical section in here. Okay, so we have our 4 processes, or our 4 cores, however you want to think about it, who all want this resource, who all want to get into the critical section and make a modification of the code that's in there. We'll throw our little yellow variable in there. Oh, it's pretty. You guys are no fun.
Well, I'm still confused because the red is clearly supposed to be memory. Because memory's always.
Oh, yeah. So what's my locked door then?
White? I don't even tell them there.
Yeah, but red means stop. Here's our fix. Okay, we got her fix. Because green means go, red means stop, right? That's okay. So we got to keep those colors. That's a fixed thing. RAM, and we just switched to a different brand. We're fine. I've seen brands of RAM that have white heat sinks. That's a thing. All right, that's one of yours. You have the white heat sinks in your RAM.
It's black, but there's LED white.
Okay. You have LEDs on your RAM.
Yeah. I don't know.
Remember how many of you have ever actually installed RAM that didn't have heat sinks on it?
Yep.
I mean, it's like, what's happened?
I don't understand they heat up.
I don't know that I don't know if I've ever seen RAM that had lights. Your RAM lights up?
It lights up. Like,
It's just a waste of energy.
They have motherboards that are RGB too. Everything you can put in a computer now is RGB.
yeah, it's ridiculous.
Is it just to have it look cool in the corner or something?
Yeah. Cases have RGB. RAM has RGB. Motherboards. Liquid cooling for CPU has RGB.
That's just being a poor steward of our natural resources.
If it's not giving you a seizure, you're giving it wrong.
It's like from Ready Player One. It's like we've decided that we could sell 80% of the user's visual space before inducing seizures. They're talking about putting advertising space up. I don't know, that doesn't even make sense. Okay, well, in any case. So we're trying to get into this critical section so we can do something with this variable. Change it, read it, whatever it is. All right, but we want to make sure we're the only one that has access to this stuff. All right, so right now this door is open. So, Here, just for the sake of my example here, we'll just use these two cores. We only need two cores to show it. All right. So both of these guys want to access this resource at the same time. Okay. So that's where our race is occurring. All right. So only one of them is going to get it. And once they gain access to this dude locks, preventing this guy from getting in. Make sense? Now, that move, the move of this guy getting that resource, opening the door, going in the door, shutting the door, locking the door, purposely making it sound like many steps, right? That has to happen atomically. Because if it happens in more than one CPU cycle, there's a chance that this dude could slip in before the door quite locks, right? And we don't want that, because now we have two elements inside of the critical space, the critical code. So, this guy here, we're going to call a semaphore. Okay. Now, a semaphore, and I think we talked about this at the high level another time. Let's just throw it back in here. I'm going to say this is kind of a special kind of integer that can be incremented and decremented atomically. So add one, subtract one, that has to happen atomically. I promise you, in terms of CPU cycles, it wouldn't happen atomically. So it needs to happen as if it occurred in a single CPU cycle. All right? So this needs to be something that the hardware supports and that the operating system backs up. Make sense? Because what we're effectively doing is we are working with our process scheduler to treat something that doesn't take one CPU cycle like it does take one CPU cycle. Okay? Now, That's an operating system piece. We don't have to worry about that. We just have to know that it exists. Okay? So what a semaphore is doing, that guy is making sure that when something grabs this resource, opens the door, walks in, closes the door, and locks it, that happens as if it occurred in a single CPU cycle, therefore guaranteeing that only one resource is in here at a time. Make sense? All right. Now, I mentioned here that semaphores are a special kind of integer. Now, integers don't have to be just zeros or ones. Okay? We might think of a simple semaphore as just being 0 and 1, but earlier I mentioned that sometimes we want to allow more than one resource or more than one thread or process to access a single resource at once. Sometimes that's okay. So semaphores, the door is locked when it counts down to 0. There's no available resources. So when this guy is a 1, when this guy is greater than 0, he's open. Okay? So as long as he's greater than 0, he's open. So the idea of opening the door, walking in, shutting the door, locking it, is that we're going to replace that idea with decrementing this guy. So he'll go from a 1 to a 0 atomically. Now the door is shut. The next guy who tries to access this particular thing can't get in because it happened atomically and the count is now 0. But if we started this count at 2, when the first guy grabs it, the 2 becomes a 1. It's still greater than 0, so this door's still open. Like a turnstile, yeah. So door's still open. This guy can now come in. He can grab that resource as well. But when he grabbed that resource, he decremented the semaphore again. Okay. So all a semaphore is an integer that increments and decrements. Okay. But it happens as if it's happening atomically. The atomically piece there is that's the special sauce. All right. Good with that? So now let's look at an example. Some sample code. Okay, now remember this thing I mentioned earlier, this thing about mutual exclusion. All right, so sometimes the idea of a semaphore only allowing things in is sometimes called a mutex, a mutually exclusive resource. Okay, so if you see that word or something like that, it's a synonym for that type of thing. All right, so this example uses our p-threads, which we've been currently working with. We're bringing in semaphores, so that special library that is using the magic of the operating system, because this is actually part of the system calls for the operating system, which then works with the hardware, because the operating system is going to support your multi-cores and stuff like that. So the magic is already occurring. We just had to know as programmers that we need to use it. Okay, so here's our critical section. All right, so this is where the magic needs to happen. Okay, this is when we might be changing our variable or reading from the variable, something like that. Okay, so we're creating something called a SEMT. Now, what kind of animal do you think this is by its naming convention? Struct. Okay, this guy is a struct. The underscore T usually means it's a struct. It's not a rule, but seems to be a naming convention. So I'm creating a variable called mutex, mutually exclusive thing, of type SEMT. All right, and this is my thread function here. So we'll pop back up to this here in a second. Let's go down here to main. So what are we doing? Well, we're going to use a function called seminit. We're going to initialize a semaphore, and we're going to pass it our struct. We're going to pass it, I think this is the number of resources we want to have. Let me confirm that for you, but 'cause I'm not sure what the 0 is. Because if we want to share it with 4 or something like that, we would make this larger. It might be the minimum and maximum value of the integer because, like I mentioned, it is an integer, But it's always, as far as I know, it's always a 0 when it closes. So that was what called Seminit. Oh, I don't want to get rid of my message passing stuff.
It's integer p share. Just something share.
Yeah, so this guy is the count, how many versions of this resource you have. If this doesn't tell me, I can make a pretty good guess at this based on its name. This might protect it across multiple threads within the same thing. P in front of it usually is POSIX stuff, so did you read that? That's what it is? So it's whether or not it's shared or whether or not this protects against threads.
Thread for process or processes.
Okay. But from what I have explained today, this piece is the important piece. How many things can access this resource at once? Okay? So our simple example is only going to be one, and that's probably our common example, right? Usually we're trying to lock down a resource and only one person can access it, but potentially we could have more. All right, so we'll initialize our Semaphore to allow up to one resource to access it at once. And then we're creating our couple of threads. This is stuff we did previous class, right? We'll create those threads. We're connecting them to our function up top called thread. This is just that thread function. Okay? And we're not passing any parameters in because we just want to prove that we can lock and unlock something, right? So we have one thread, and then we go ahead and tell this guy to go to sleep. Probably didn't need to do that, but whatever. So we have a thread. We're going to sleep for 2 seconds, then create our second thread. Then we're going to wait for our 2 threads. That's what the join does, right? Waits for them to finish, and then we destroy our Semaphore. Fine. Not a whole lot of crazy stuff going in there. The only new things for us is creating the Semaphore and dumping the Semaphore. And this guy's just using a sem-type mutual exclusive thing. If we want to look at that sem_t, let's see if we have a man page for that. Nope. Oh, looks like it's just an int. So actually, in that case, it actually isn't a struct. It's a type def. So it's effectively creating a synonym for int called a semt. All right, which supports this idea that it's a special kind of integer, but it's literally a rename of int. All right, so 2 functions and an int. Walk into a bar and all right, so this is where we create the Semaphore, and there are 2 threads are going to use it. So, well, I'm sorry, we create our Semaphore down here. Then our 2 threads are going to use it. So both threads are spinning up this code. So what happens here, this is us closing the door. Okay? So when we do a sem_wait, what we're attempting to do is we're attempting to do a decrement on the Semaphore. Now, we're only allowed to decrement the Semaphore if its value is currently greater than 0. Okay, I mentioned it'll only let you in if its value is greater than 0. Okay? So we're going to wait until the value of this guy is such that I can decrement it. As soon as I can decrement it, then I will decrement it, in our case here, locking it down. Say I am in the critical area, whatever, I can do all my magical stuff, and I've decided here that my magical stuff is going to take 4 seconds, okay, which is a lot, okay, so I'm basically chilling in this area, right, for 4 seconds, I'm just hanging out in here doing nothing, all right, just, I guess, being a jerk, all right, then at the end of that, now I'm going to say, okay, I'm ready to leave, and that's when I post, so this increments. the semaphore. That make sense? All right, so that guy's incrementing and decrementing. We're waiting 4 seconds here. So if we kind of follow along with what will happen here, we're going to create our first thread. Okay, now this guy is going to immediately start spinning this, right? This guy's going, we'll decrement our semaphore from a 1 to a 0, and he's going to come in here, he'll print something, which takes some time. Anyway, so we're not just waiting 4 seconds. We're also doing two context switches while we're in here, just for the fun of it. Okay, so we'll context switch with some I/O here. Then this dude's just going to go to sleep for 4 minutes, 4 seconds rather, and then we'll do another context switch. So while that's happening, so let's pretend these guys happen instantaneously. This we're going to be waiting in here for 4 seconds, right? But we only slept for 2 seconds here. So 2 seconds later, after the first one started, the next thread was created. So there's still 2 seconds left in the clock. All right, so this guy will spin up. He'll come in here. He will try to access this semaphore. He'll try to decrement the semaphore. Won't work. Now, internally, what's actually happening here, and I think on different operating systems, the time is different. It's actually checking back. So it's not just sitting there pinning it. You know, decrement, 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 decrement. It's sitting there and saying, okay, this didn't work, so I'm going to come back and try again. And usually it's some kind of random number thing. And what's important, well, why is that an important thing to know? That it doesn't just let him in at the exact moment he can get in. He has to check back to try to decrement that. What implication does that have on programming with semaphores?
Put a load on it? Because just asking, keep it asking.
I'll give you a hint. If we have more than 2 people trying to access the same resource, let's say we have 20 people trying to access the same resource, but there only one person is allowed to access it at the same time. The fact that when somebody tries to decrement it, they are effectively turned away, and then they have to come back after some random amount of time to try to decrement it again. What implication does that have?
It's not first come, first serve.
Not necessarily first come, first serve. We don't have a guarantee that just because you try to get that resource second, that you will get that resource second. You might. you might get it second. But typically, a random number is generated. A small. I mean, you're not waiting a whole lot of time, but a small random number. And if somebody else's number happened to be enough smaller than your random number to bridge the gap between the amount of when you arrived versus when he arrived, he might actually hit that resource before you can. That make sense? So under, let's call it a rare situation, we might actually create a situation of, I would call it deadlock-ish. Because if you have 1,000, the more we up the number, the more probable this becomes. If we have 1,000 things all trying to access this resource at the same time, okay, and those 1,000 things are all running again at the same time. So we don't have a space 2 seconds apart or anything like that. We might create this situation where one guy never gets access to the resource until everyone else is done. He might be last, even if he was the second one there. Does that make sense? And if the guy inside sleeps for more than 4 seconds, maybe he sleeps until some condition is met. So you're grabbing some resource, you're grabbing the Bitcoin wallet, and you're waiting for the price at Best Buy for some TV that's currently $5,000 to drop to $5, which might take a while. So you're going to be sleeping for a bit. So then all of a sudden you've created a situation where a resource is now completely locked down. Nobody else can access that resource. All right, so that makes some sense? All right, let me try to run this guy locally here. I put this on the desktop. Let's just see if it runs on the Mac as is so we can see this. So the expected behavior we would see out of this is a thread is created. We see, he'll immediately get the resource. We'll see entered. 4 seconds later, we'll see Jess exiting. In the meantime, 2 seconds after the first one started spinning, another one is created. He's going to be knocking at the door. Immediately after we see Jess exiting, we should see him saying entered. right? Because he doesn't get to get in. He's waiting here for 2 seconds before he's able to finally decrement. Well, at least 2 seconds. Till he's finally able to decrement and enter this critical section. Then he'll wait 4 seconds and finally say just exiting. All right, so this is desktop and it's called SemExample. Oh, that's not going to work at all. I don't need to use pthread. I do need to use a, I think it's a -mutex thing. This guy should tell me the flag. Oh, it does want me to use pthread. Oh, because it's not the semaphore that's breaking, it's the pthread that's breaking it because we're using pthreads.
I hope if you type feedback.
Oh, really? Isn't that how you spell pthread?
Yeah, but I don't think it's an L in it.
Oh, is it just -pthread? I thought that we were linking pthread.
I just passed it as an argument, that's all right.
All right, so maybe this won't work on Mac, but we've seen it work on the other one. So we'll come back on Monday. I'm going to introduce cues, but we'll probably do that the second half of the class on Monday because we're going to interject this code into ours. We know pthreads will compile on, in fact, I think I saw before pthreads won't compile as is on, actually I need to do a sudo, right?
I didn't have any problem with pthreads compiling on my machine. And I didn't use sudo, but you could try it. 'Cause I don't know this is
Let's just try it real quick.
It's just a warning though, that it's not actually run.
Oh, I guess that is true. See, that's actually interesting. The second guy was allowed to enter before the first guy was able to exit. And is that a nature of the context switch?
I didn't see you
Yeah.
actually decrementing.
So, oh, yeah. Okay, so let's look at that on Monday. Then we're going to put it into our chat server, so we can protect that resource. And then we're going to look at message queues. All right. I will see everybody on Monday. Remember, if you're doing the hackathon, we're meeting on campus by the Circle Drive flag tomorrow at 8:25 a.m. If you have a Concordia shirt, wear it.